Okay. Um, so I want to start off by welcoming everybody. This is our second year of having a ocean acidification research update session at the Alaska Marine Science Symposium. And my name is Darcy Dugan, and I'm with the Alaska Ocean Observing System, and I'm the director of the Alaska Ocean Acidification Network. And I think I've had the pleasure of working with everybody here on this call so far. And we'll get to meet many of the researchers in the network over the course of the next 2 hours. I want to take a moment at the beginning to acknowledge that this morning I'm on the traditional land of the Dena'ina people, and the work of our network spans the entire state of Alaska, which is the traditional home of many Indigenous peoples. And we'd like to give our respect and gratitude for our ability to learn and work on this traditional land. The goal for our session today is hopefully provide a space for researchers to share and hear what they're doing, which will help all of us improve our understanding of what's going on in the world of ocean acidification, and also be able to strengthen our collaboration. And there's 18 researchers on our lineup today. And I was reflecting last night that 5 years ago, when our Ocean Acidification Network started, there were a handful of researchers that were really focused on ocean acidification. And now this community is really growing. And I think this speaks to this growing area of research and interest in Alaska and commitment of the science community. And I think ocean acidification research in the past has been referred to as like putting headlights on a car. And I think due to the work of all of you, the headlights are getting brighter here in Alaska. I think we can use this opportunity today to look for not only learning what other people are doing, but also look for ways that we can work together. So I encourage you to please note during your updates if there are topics where you're looking for collaboration, or if you could use help, or if you could provide help. I think our network is here to help support one another. And part of the strength is that it's really interdisciplinary. There are so many specialties of people on the call right now. And that's wonderful. Our format for today, each researcher will have up to 5 minutes. You don't have to use your full 5 minutes. When you're closing in on the 5-minute mark, I have a handy little bell that I will make a little ding so that you know that it's time to wrap up. And if you're coming up next, you should be prepared to share your screen. I think it should be, we'll have time for 1 or 2 questions after each talk. And so as soon as you're finished presenting, go ahead and stop sharing, and the next person can begin their share while the questions are being asked. If you have questions for speakers, please put them in the chat. And we'll run off those. And if there's more questions than we can answer in the period immediately following a presentation, dialogue can continue on the chat. If you just presented and you see questions for you that you didn't answer verbally, feel free to put that into the chat where everybody can see it, and we'll also write them down for later follow-up if we don't get to everything. As I mentioned, I'm recording this morning, and the recording will go on the Alaska Ocean Acidification Network website for those that aren't able to join us this morning. So, I wanted to note before we dive in, 2 changes to the agenda that I sent out earlier this week. One is we added Claudine Hari. She's going to go after Natalie this morning, I think like 5th on the list. And then I scooted up the salmon tipping points presentation because they had a conflicting meeting later this morning. So they're going to go after Chris. So I think with that, I will pass it off to Cale Miller from UC Davis, who will be talking about Beaufort Lagoon monitoring. So I'm going to stop sharing. And Cale, if you want to pick that up and take it away.
Sure. Thanks, Darcy. Let me get over. I have multiple screens. Hold on 1 second. Okay, can everybody see my screen okay? Looks like.
Yes.
Okay, great. Yeah, so I'm going to talk to you today about a long-term calendar year pH time series that we have in Kaktovik Lagoon. So we are here up off the north coast, pretty close to the Canadian border. You can see Kaktovik Lagoon is pretty isolated, just a few small channels out here to adjacent lagoons and then to the greater Beaufort Sea. And this is a part of the Beaufort Lagoon LTER. And the Kaktovik Lagoon is pretty shallow. It's about 4 meters depth. And then this whole lagoon does become landfast ice. So it becomes completely covered in ice. But we were able to have a sensor in there for the entire calendar year. And we were trying to describe the dynamics of the pH and maybe some of the drivers of that. Okay, hopefully my computer doesn't go slow the whole time. So this is what our time series looks like. So we have pH in our top panel here, temperature, and then salinity. And then this is starting in August 2018, going to August 2019. These dashed lines here indicate the different seasons. So we have our ice-free 2018 phase. We have our iced or our closed phase 2019, 2018, and then our open phase 2019. So some of the highlights that I just wanted to point out here were just the extreme variability that we saw in pH. In 2019 and 2018, we saw rates changing, hourly rate changes that exceeded 0.4 units. So pretty dramatic, and it was kind of tough to find similar rates of change in the literature. And then the other highlight that I wanted to show you here was that in our running average that we calculated here, there was about a 0.2 difference in August in 2018 and 2019, with August having a higher pH. So just showing you that the difference by months by year, or in the same month by year, for our year-long time series, at least for this time period that we covered here. Temperature isn't really doing much. It's just kind of following the seasonal trend here. We did have a lot of variability in salinity in 2018 compared to 2019. Kaktovik Lagoon doesn't really have a lot of large river inputs, but it does have small tundra streams. And you also do have a lot of storm activity, especially in the fall season. So this time here compared to here. And I wanted to talk about the relationships with salinity because pH, relationship with salinity, actually in open phase 2018, we didn't really find any. So we had a lot of salinity variability, but we didn't really see a correlation at all with pH that existed. We did have a negative relationship here with a pH decreasing with a salinity increase. And then for 2018, we had a positive relationship here between pH and salinity. So something that you would more expect to see compared to what we saw here in 2018. But we were able to measure underwater PAR. And what we do have, you can see here that we have daily average pH here. This is for 2018 and then 2019. You start to see when we get some peaks in PAR here, you do see this daily average pH signal actually bump up. So we do have a pretty strong correlation or indication that there is some strong photosynthetic activity that is really kind of bumping up pH when PAR is available and ready. And these are pretty strong correlations between daily average PAR and daily average pH. So in 2018, we had 0.46 and then 0.64 during these open phases here. And one of the last things that we wanted to do was kind of characterize the CO2 flux to the atmosphere. So this top panel is 2018 and then 2019. We were able to take atmospheric CO2 measurements from Utqiagvik. So this is about, I think, 300 kilometers or so to the west of where we were in Kaktovik. And then the big difference here is that so everything positive is flux to the atmosphere. And for 2018, even though we had really strong winds, which you can see here in this gray line here, we didn't really have strong flux at all occurring in 2018. However, in 2019, we did see that we had strong correlations between our wind and our atmospheric flux to the atmosphere. And this had to do with because there was a larger disequilibrium in our baseline pH value in 2019 than there was in 2018. So even though we had strong winds, if we didn't have that disequilibrium between the atmosphere and the sea, then we didn't really see too much of a flux here. And it's important to kind of highlight these because we are able to calculate an average calendar flux of 1.7, and some of Wiley's work has shown that the greater coastal Beaufort is a sink for negative 2.1, but just showing you that these lagoons are actually pretty different than the greater Beaufort Sea. And that's all I have.
Great, thank
I'm
you.
at 5 minutes, so I'll stop sharing.
Yes, Darren, if you want to queue up yours. Are there any questions for Kale?
Kale, this is Wiley. I was just curious how you computed PCO2 from your pH.
Yeah, so we had 3 alkalinity samples, and I know it's not very much. We did have a really strong R squared value, and some of our regressions that we calculated, we were able to calculate, or the regression we calculated were pretty similar to some other salinity, alkalinity regressions in the North Atlantic coast. So um, I can talk to you more about that later if you're interested, though.
And Kale, you just had a publication come out, right?
I did, yeah. So Amanda and I, we had a year-long time series in Jackalope Bay and Bear Cove that just got published in LNO last week. Um, and this paper with the Kaktovik Lagoon data is uh, uh, it's in review right now at Biogeosciences. So it's up on the discussions, so you can actually take a look in the reviewers' comments and everything.
Great, thank you. Yeah, thank you for that presentation. Darren, you're up next.
Great. Can you hear me and see this okay?
Looks great.
Okay, awesome. So yeah, over the past year, I've been working with colleagues at the University of Washington and PMEL, continuing to develop our capabilities with this regional model for the Bering Sea to simulate carbon chemistry. You can see here that, for instance, we combine the physics, the biology, and the chemistry to kind of couple this all together to be able to simulate processes like saturation states, pH. And this year we've updated our kind of long-term historical hindcast all the way to mid-August, as you can see in this animation that's been playing at the bottom here for surface omega. So as part of this,
I'm gonna go ahead and mute everybody, and then you might have to unmute yourself, Darren. There we go.
And so as part of this updated hindcast, right, we've kind of expanded it to nearly 2 decades at this point, so we can sort of start saying a little bit about more of the long-term conditions that we're seeing simulated in the model, as shown in the top left here for summer bottom water conditions, showing the spatial heterogeneity between a relatively more buffered inner shelf bottom waters versus more getting to a corrosive state on the middle and outer shelf, particularly when you move north and west up towards the Gulf of Anadyr. And so with this information, then we can now kind of take this and say, okay, well, how did this summer compare to that more longer term average to sort of illustrate, right, how the middle and inner shelf is sort of a mixed bag between how this compares to the long term, but the outer shelf, this is suggesting, was a little bit lower in omega overall for this summer at the bottom. And so what we're doing with this information is working with colleagues in fisheries to really start supporting fisheries management. And so this year we did this by sort of developing and initializing an index value for bottom water conditions shown on the top left here. This is like the percent of the total Bering Sea shelf, or at least the US side, that had waters with an omega less than 1 during that summer time frame. And of course, stretching back all the way through our hindcast. So illustrating not just the long-term processes that we'd expect, but also the interannual variability. And you can kind of tie it to some of the natural variability that has occurred over this time. For instance, this index kind of peaked right in 2013, which of course is kind of right at the tail end of the cold period, and has sort of recovered a little bit since then as we've moved into warmer conditions again. And so this information was used in this year's ecosystem status report that just came out yesterday, I believe. It was a noteworthy section in that that kind of explains sort of this process and where we're moving forward. It also was included in the newer ecosystem and socioeconomic profiles for Bristol Bay red king crab and St. Matt's blue king crab. And so, right, one of our points with this, and I highly encourage you to check out this noteworthy section to learn more, is that we're really open to feedback on this as well, that this is just a very kind of mock image of what we're expecting or what we're trying to do moving forward. The idea here is that this will turn into more of an annually occurring indicator in the ESR, and that we can kind of continue to develop that. And so lastly, I'll say too that we're also trying to work on the capability to forecast this on sort of 4 to 5 month timeframes in advance. This is based on work that colleagues at the University of Washington have already done with regards to forecasting the bottom water cold pool. What they found is essentially the forecast skill is pretty low until you initialize after the spring ice retreat. So anytime you start your forecast before the ice is just too unpredictable at that point, and you just can't get predictive skill in the bottom cold pool. But if you start after the ice, say in April or May, you can get some predictive skill with that. And so we had actually planned to test this for the carbonate chemistry this summer, or this previous summer, in connection with a NOAA fisheries cruise in the summer. However, that was canceled due to COVID. And so we're still going to be coupled with fisheries moving forward in order to, make a forecast and then actually compare it to the field data for that year. It's just that plan has kind of gotten on hold, and we're sort of going to have to go backwards and kind of work on reforecasting previous years like 2008 to 2010 to get a better sense of the model scale for forecasting the carbonate chemistry. So we have kind of a lot of work in plan with that right now. I just ran those reforecasts. Actually, I haven't had time to look at them yet, but I guess stay tuned for that moving forward, potentially at next year's meeting.
Great, thanks, Darren. I put the link to the ecosystem status report website in the chat there. And want to mention Darren gave a great talk on this on the AMSS panel on Tuesday on multi-stressors and how the information that we're gathering through science is being used in management. And Yvette Sidden with NOAA, who compiles those, or is part of a team that compiles those ecosystem status reports, followed up on that panel to describe more about how it's being used. And I think being able to put ocean acidification data and science in the hands of managers has been a goal for a long time. And it's exciting to see this starting to happen. And I think something that our network can do is think about what other data is ready for those reports. Let's see, I see a question from Chris. I guess while Darren's answering, Jessica, if you want to get queued up, that'd be great. How do you expect the fishery managers will use the forecast products?
Yeah, that's a great question, Chris. So right now, right through the ESR, it was already kind of in the pipeline for eventually, right, the council kind of making, or the SSC sort of delivering science information to the council. I know it was presented to the council, and there was a lot of interest and a lot of great feedback that we got through that process in terms of like how we can continue to develop it, how we can do a better job of showing how it compares to the observational data to make sure that the model has some skill with that. And so, right, ideally, I think as we kind of get this narrowed down a little bit and firmed up, that it'll just be a piece of information that we can continually produce that can be put into the fishery management pipeline, through primarily our colleagues at fisheries, such as Yvette, as Darcy mentioned.
Yeah, that right. Yeah, I'll follow up with you. I'm curious what they're looking for. Maybe that'll be a discussion with the group later, just like which folks on the fisheries industry side are particularly interested around which species, but that's a longer conversation. Thanks, this is really great work.
Thanks.
Chris,
Darren,
oh, go ahead.
Darren, I'm wondering if you could actually tee me up a little bit to start my presentation and talk about how you're working to maybe expand this approach into the high Arctic, the work that you're doing with Nadia.
Yeah, sure. So Nadia Steiner is a researcher at Department of Fisheries and Oceanography Canada, and she has more of a pan-Arctic model that also includes part of the Bering Sea. And so what she's really interested in is kind of linking our two models together, because right now the the kind of difficulty with these regional models is you need to know what's happening at the boundaries. And so for her model, she needs to know kind of what's happening in the northern Bering Sea. And that data to get some of the chemistry boundary conditions, as we know, working in the Bering Sea for our northern Pacific boundary, is very limited and very difficult. And so the idea and the hope is that by integrating our model with hers, we can kind of improve that skill and then, you know, kind of have this moving forward as more of a coupled system between the two.
All right, thanks a lot, Darren. I wanted to structure my research update today just in terms of the field program that we've got going right now. You'll be able to hear a lot about the work that, you know, our group that Darren and I are leading at NOAA and UW through the research talks at AMSS. And so I thought that it would just be redundant to share all of that with you. And so everything that you're about to see is a very rough sketch of what we're working on and what our broader research questions are. So in 2020, we were very lucky to be able to get up to the Beaufort Slope in conjunction with a Woods Hole cruise on the Sekuliak. This is the map of samples that we were able to take with the assistance of Lori Juranic. And again, you know, part of the goal for us in taking samples up in the high Arctic is to be able to capture you know, the transport of carbon that's happening sort of around the Chukchi Sea and moving into the Beaufort Sea. These samples are also going to be really valuable for Nadia and the Pan-Arctic model that she's got going because they cover this cross slope. They cover this cross slope area, cross shelf area, and that's going to help her resolve a little bit more of her boundary conditions. It's also a priority for NOAA to be able to work closely with our Canadian colleagues. Even though this is US territory, it's going to benefit both of our countries to be able to reduce the uncertainty in this model and better understand, use those models to better understand spatial variability in the Bering Sea, the Chukchi Sea, the Beaufort Sea, and in the high Arctic. I also wanted to give you an update about what our 2020 plans were, or what our 2021 plans are. As Darren said, we have ongoing work with the NOAA Fisheries Program, where we're going to be collecting DIC and TA samples in conjunction with the NOAA Fisheries Stock Assessment cruises. And I'm showing the grid for that here on the left-hand side. As Darren said in his presentation, we had essentially planned to do the exact same sort of survey in the Bering Sea in 2020, but unfortunately that was canceled due to COVID. But we'll now be sort of switching from a model where we do a dedicated biogeochemistry survey once every 4 years to being able to collect samples in either the Bering Sea or the Gulf of Alaska every year. So as many of you know, the Bering Sea and the Gulf of Alaska alternate, with Gulf of Alaska during odd years and Bering Sea during even years. So we'll be collecting samples on this grid in 2021. And then in 2022, we hope to get back to the ESR grid that Darren showed in his presentation in the Bering Sea and contributes to model development and validation of his forecast in 2022. I wish it could happen faster than that, but unfortunately we just don't have the survey time until 2022. The figure that I'm showing on the right-hand side has been a survey that we've planned to do since 2019, but is absolutely cursed by every malevolent god in the universe and cannot get done. So unfortunately, due to COVID, that cruise is going to be delayed again until next year, just because we don't have the infrastructure to support a cruise during COVID times. But our goal, again, is to be able to assess this kind of cross-shelf variability, especially towards Southeast Alaska in ocean acidification parameters. So big red X. Unfortunately, we won't get there. Another big red X in 2021, we had also planned to join the harmful algal bloom survey, which I think is going to get an update in this research session later, so I won't talk too much about it. But Woods Hole had planned, has also been planning for several years to try and do a mission up in the Chukchi Sea that assesses harmful algal bloom cysts in the sediments. And we were going to collect samples on that survey in order to try and contribute to research about how acidified conditions may be contributing to the toxicity of blooms that are caused by those cysts. Again, we're going to hear a lot more about that later in this session, so I don't want to speak out of turn. But preliminary research shows that acidified conditions can make harmful algal blooms more toxic, if not more likely. And this mission is designed on our part to try and contribute to some of those research questions. So we will be participating in the EcoFoci Fall Mooring Survey, which will be combined with some Arctic work this year due to COVID, where we'll be able to collect some samples along the 70-meter line, as well as some of these DBO areas. A very rough sketch of what that will look like on the right-hand side is shown there. So we'll get a little bit of data that can contribute to the validation of Darren's model, but certainly not nearly as much as we would get with the robust CTD sampling from the ESR mission that will happen in 2022, validating Darren's model. The big work that we'll do in 2021 is that we're hoping to fill a bunch of surface PCO2 survey gaps with some sail drone work. So what you're seeing in the background here in the open circles is the result of a synthesis for surface PCO2 data in the Bering Sea that was conducted by a UW postdoc, Hongji Wang. And what it found is that there are pretty significant gaps in where that surface PCO2 has been collected. And so we hope to be able to use a sail drone this year to fill some of those gaps. And we're doing that for two reasons. One of them is that it promotes equity. A lot of our community outreach has indicated that, you know, what people really want to know about is this more of this near shore area and you know, some of these major fisheries management areas. And as you can see, the surface PCO2 in those management areas and common fishing areas like Bristol Bay is really just totally absent. And so we're hoping that by collecting these samples, we'll be able to better validate Darren's model in these regions, which again is going to be our primary tool for assessing some of their questions. But also it's good for science, right? We can't really resolve the seasonal flux in the Bering Sea without a much better idea of what's happening at the near shore, and traditional ships are not very good at doing that. So we hope to be able to get a better sense of the summertime seasonal flux by moving forward with this mission this year. In the long term, I want to encourage everybody on this call today to keep an eye out. I think the next big topic that's going to be facing us is carbon dioxide removal. This is something especially that the state is pushing really hard towards, and that the commercial fishing and subsistence communities are working really hard towards. This idea that we might be able to mitigate ocean acidification using macroalgal farming, among other approaches. We don't really know if those are going to work yet, but there are ongoing studies in a variety of areas around the world, as well as the United States, and most specifically, we're trying to scale one up in Kodiak in partnership with industry and tribal research partners. And so I would encourage you that as you have the opportunity, get in on this on the ground floor. Congress is excited about it. Everybody is excited about it. The tech bros are excited about it. Elon Musk even tweeted that he was going to put $300 million towards it very recently. No details about that prize yet, but I would be surprised if this doesn't become a major new research avenue for us in the next 5 to 10 years. You can find out more at AMSS. The end.
Thanks, Jess. Wow, well, maybe that carbon dioxide removal might be a good topic for a future webinar discussion through the network of kind of sharing what's going on, more specifics of what's going on with the Kodiak project, and kind of for a lot of people, like what that even means. So stay tuned on that. Also, in addition to the big red X's, that's exciting to hear about some of these new partnerships that are going to maybe provide us with additional, that co-locating of biological and oceanographic data sounds really valuable. And then I also just wanted to mention, I just want to thank both Bridget Ferris and Yvette Sidden for both being on this call right now. They are these champions that are pulling together all of the information for the ecosystem status reports. And as we talk more about what other ocean acidification information should go into there for the council, we'll be working closely with them. So to both of you, and I think many people might be on those conversations coming up. Let's see. The next presentation is the work of Natalie Minacci, who is not able to be with us today, and she sent me a few slides, so I'm going to share those. Let's see. Okay, are you back to seeing that title page? Yes. Okay. Oops. There we go. I'm going to run through a couple of her slides. She noticed that Jessica Cross might be able to answer questions about them. I haven't asked Jessica, but hopefully she can. So this is highlighting the results from two surface moorings on the GAC OA, which is located outside Seward in the Gulf of Alaska, and then M2 located in the southeastern Bering Sea. And they're collecting carbon dioxide observations and tracking variations in the timing and the strength of the spring bloom. And Natalie mentioned that pH measurements are still sparse, that the critical parts, the production of the critical parts that are needed for the seabird CFET pH sensors have been slowed and in some cases stopped. So that's been a challenge. Let's see. There we go. So this slide is a graph of PCO2 at the GAC OA mooring. Along the x-axis is time and months, and y-axis is the partial pressure of carbon dioxide in microatmospheres. And the blue line across the top is the atmospheric PCO2 content that's measured at 1 meter above sea level. And the solid black line is the final 2019 seawater PCO2 data that's measured a meter below sea level. And you'll see those dashed lines are the minimum and maximum seawater PCO2 that were measured between 2011 and 2019. And you'll also notice the big dip in April and May, and that's because of the spring phytoplankton bloom that's drawing down the surface PCO2 from what during the winter is near atmospheric values and then to a minimum concentration for the year. And the 2019 surface spring bloom at GAC OA was slower, later, and weaker than in previous years. And Natalie also highlights here that the minimum value for the entire record was in spring of 2018. The next slide adds in 2020 data. So the solid black line is again the 2019 seawater PCO2 data. And now the red line is the preliminary data for 2020. And a question she asks is, was the spring bloom in 2020 the earliest in the record? And it certainly appears to be faster and stronger and earlier than in 2019. She also notes here a big spike back up to seawater, higher seawater PCO2 values on April 9th, and that coincided with 40-knot winds that were measured about 15 kilometers away at Pilot Rock. So explanation for the data there. Those instruments will be recovered in March, and Natalie is hoping that the final data, the process data, will be available within a year. And then moving over to M2 and the Bering, that's the yellow dot at the bottom of the screen. This mooring is only deployed from April to October. And again, air is the blue line on top, and the final 2019 seawater data are the solid black line. And like the other graphs, those dashed lines are the minimum and maximum observed over the entire record. And she noted that they missed the onset of the spring bloom in 2017, and that the spring bloom in 2018 was the latest and the weakest in the record. And that 2019 had a fast and strong spring bloom compared to other years, but then unfortunately, they quickly lost all the data due to a massive equipment failure, which was likely caused by seals. And the 2020 deployment of M2 was unfortunately canceled due to COVID. And then this is the last slide. OARC is offering a student opportunity to add OA measurements to student summer 2021 research projects. And so they're offering students to collect up to 20 samples and the lab will run them for free. And so if you're working with students or know of people that could take advantage of this opportunity, to contact Natalie to discuss details and requirements for collecting the samples. And one-page proposals are due by March 15th. And I'm going to post this on the Ocean Acidification Network website and Facebook page as well. There's a flyer for it. So that was Natalie's update. I'm going to hit stop share. Oops, let's see. There we go. And if anybody has questions, I'm hoping Jessica might be able to answer them. Any questions on Natalie's presentation? Okay, great. And it looks like, oh, you know what, Chris, I mentioned in the beginning, and I was probably before everybody was on, I was going to slide Claudine in there just to kind of continue with our geographic and open ocean.
Sounds good. I just stopped sharing.
Awesome, thank you. If you would be ready to go after Claudine, that would be perfect.
Can you see it?
Yes.
Hi, everyone. Yeah, okay.
It's not in presentation mode, but we can see it.
Okay. Is that better?
Yes, perfect.
All right. Great. Hi, everybody, and thanks for squeezing my presentation in. I'm just going to give a quick update on what our lab has been up to. My lab now consists of a technician, Rita Irving, and then a postdoc, Remy Paget, who just started past August. Unfortunately, he's still in France because of the visa issues. And some of you might know too that I'm still in Switzerland because of COVID, but we're hoping to come back to Alaska in June. And so, I don't know, maybe some of you have seen my presentation at AMSS on the Gulf of Alaska biogeochemical model, and also just gave a webinar. And so basically, I just want to let you all know that we have a 34-year-long hindcast simulation now available online. And it's you can really easily use it with this interactive model web tool. And, you know, besides ocean acidification parameters like pH, aragonite saturation state, DIC, and alkalinity, there are a bunch more variables that you can just look out. You can look at the surface or depth variables. You can look at the time series like this Hoffman plot over here. And I just welcome you to play around. I didn't put the link in here because it's a little complicated, but it's on my website and it's my name, Claudine Howie at orjust.com, and the model tool will be easily found there. And we just also published a paper so on the model, and if you have any questions about evaluation or so on, just let me know. And let's see. Oh, yeah. And so my lab is not just doing biogeochemical modeling, we're also taking samples and we're analyzing them for alkalinity, DIC, and pH. And we took over the Seward line analysis and sampling back in 2019. And so we're analyzing, depending a little bit on the funding so far, we didn't get that much funding yet, but I hope this will, or it will probably change starting this spring. We're so far just sampling along the Seward line every other station, but we're still trying to figure out how to get more funding to actually sample all 4 lines along the LTR grid, which would be amazing for, like Jess mentioned, very important for model evaluation, but also just to get a better understanding of the carbon dynamics in the Gulf of Alaska, like it is in the Bering Sea and so on. And then we also started a new ecosystem observatory in the Gulf of Alaska. You might already have seen some of the data up in the Chukchi Sea, but this one is new. It's also on the Seward line, kind of like mid-line on the shelf still. And I'm responsible for the PCO2 and pH sensor there. Those sensors are located at 22 meters. And so the observatory consists of 3 different moorings. with a large variety of parameters measured, nutrients, salinity, temperature, of course, PCO2, pH, zooplankton, radiation, and so on. And so here, I just tried to quickly see what you were presenting, Darcy, on the OARC mooring, but we also see the phytoplankton bloom here in early May, and then you see very high PCO2 in winter due to remineralization. And unfortunately, even though we do have PCO2 and regular, or usually also pH, but Seabird wasn't able to deliver it on time. And so we had to set out that first year, but both of the sensors are in now for the second year, which is exciting. Hopefully it will work. And then we're also part of a bigger team to develop a carbon dioxide sea glider. And this has been kind of on hold, not just because of COVID, but also because our first industry partner, Kongsberg, went through a little bit of a restructuring, but we have a new team now. And so we're back on board, and we're now working with Advanced Offshore Operations and 4H Jena, which 4H Jena is a new company that is now responsible for the Hydro Cs, the Contros Hydro C and the Hydrofia TA and all these instrumentation. So it's great to be working with them. And then Alutic Pride is also part of the team. And Jeff, I will actually contact you later on, because now we are back on track to finally do our first sea trials in Seward, hopefully this fall 2021. And here you basically just see an image of the sea glider and where we are currently installing the Hydro C, which has a different form factor, so that the typical Hydro C is pretty big. And so we're working with 4H Jena to make it shorter, but bigger, so it has a larger surface area. So hopefully the response time will be a little bit faster. And so we're still working on the details for that. But that's pretty exciting. And then, oops, that was wrong. And then moving up to the Arctic, I also have a Pan-Arctic model going there, a biogeochemical model with all inorganic carbon parameters. And there it's a gigantic model, so we're not able to hindcast complete like 30 or 40 years like I did for the Gulf of Alaska. Here we are currently just doing 2 different time windows, one for 1980 through 1984, and the other one for the last few years from 2015 through 2019, which is nice because it overlaps with a lot of the observations that are coming in. And so here it's just you see DIC and alkalinity for some year. I don't even remember anymore. I'm just starting to analyze the output right now. And then the last project I want to show you is the Chukchi Ecosystem Observatory, kind of like the same principle like the Gulf of Alaska one. This has been in the water for quite some time. I think the first time the observatory went into the water was 2014, but PCO2 and pH went in for the first time 2016. And so we now have a 5-year-long PCO2 time series. Unfortunately with pH, it doesn't work always all that well. And also there we had some delivery issues from Seabird, but yeah, the data set or the time series we have so far looks really cool, and we're working on a very exciting paper at the moment. And I think that's it from my side. Thank you.
Great, thanks, Claudine. Your work is covering a lot of geographies of Alaska. I also particularly want to thank you for connecting this morning from 10 time zones away. So we appreciate having you.
I'm sorry, I was a little late. Yeah, it was a crazy week, but yeah, thank you.
Thanks for being here. Are there any questions for Claudine?
Claudine, can I ask a question real quick?
Sure, yeah.
Yeah, so the CEO mooring that you put in on the central Seward line, you said that you had installed your sensors at 22 meters. I was wondering if you were targeting a particular process at that depth?
No, it's more, because we have so many different instruments down there. So we had to kind of like find a solution that works for all the different parameters. And then
with us.
Right. And then with the waves, the wave action and all that. And so 22 meters was just kind of like, we didn't want to have it at the surface because it would be too rough. And, it would come out of the water all the time. So you would have issues with air bubbles and so on. And then, yeah, it's not perfect. I wish I could have 1 or 2 more sensors at different depths, but maybe in the future.
Yeah. Jessica, normally 22 meters is inside the mix layer. It's at the lower end of it, but Seth won't allow us to put the sensors up any higher. He's just afraid they won't survive the deployments if they're more like the 15 meters we'd love to see them at.
Yeah, I mean, it's going to be really cool to be able to compare then that, what is essentially surfaced mixed layer data with the OARC mooring at the GACOA site. And so it'll be really interesting to see these 2 different regimes, sort of the middle shelf and the really near shore. So
don't forget about the eluted ride percolator CO2 data as well.
I'm feeling
and then we'll add something downstream here too. Hey, Claudine, this is Chris. I had one other question, which is, and looking at the biogeochemical modeling in the hindcast, that we were just talking about that in the modeling group for the NOAA Climate Fisheries Initiative. And just curious, are you talking with Charlie Stock at GFDL about that at all? Or working with him on that?
Yeah, so he has been a close collaborator from the start of the project.
That's what I thought. Okay. Yeah, because he's bringing that into the CFI. Yeah.
Yeah, because cobalt is his model. And I didn't mention that. I didn't go into any model details, but it's RUM's cobalt and it's his model, and he still is a close collaborator.
Yeah. So hopefully that is getting some traction on a integrated for us NOAA-wide modeling initiative linked to fisheries. So that's exciting.
Okay.
I need to tell some of my NOS colleagues that this exists, I think.
Yeah, maybe we should chat offline at some point. I will be interested.
Sounds good.
Okay.
Great.
Thank you.
Chris, would you like to, Chris is with the NOAA Kasitzna Bay Lab and is going to be talking about long-term monitoring and multi-stressor assessments. So.
Yeah, thanks, Darcy. Can you see the screen?
Yes.
I have the other version of Zoom, so it's a little great. So so it kind of in the theme here, and that what Jessica I think was just talking about, the synthesis. So we have the the coastal nearshore estuary piece in the same area, right? Because we are downstream from the GAC1 mooring and the Seward line and those measurements. And so I'll show you, I just wanted to show you and maybe remind folks about some of the long-term monitoring that's going on in Ketchmack Bay. And both with work that we've been doing out of our NOAA lab, as well as what the Ketchmack Bay National Estuarine Research Reserve is doing, and that Amanda, and now with your comment about the mitigation stuff, also then with Brenda Konar on the kelp side. So just kind of giving you a flavor of what's going on, and maybe some thoughts for future collaborations and intersections on this nearshore side. So on the satellite image here, they're showing the sites of, so all the stars are where Amanda Kelly has long-term now since October of 2017. CFAT, CFOX, OA, carbonate chemistry sensors, sampling every 3 minutes for the most part. And then some of that work has already come out, and Kale and Amanda's paper is out in LNO for the Jackaloff Bay work, which is exciting. At the locations with the yellow stars and circles, that's actually where we also have long-term oceanographic monitoring. At Homer and Seldovia goes back to 2001. So there's a context here that we can put the more recent measurements in from the long-term climatology. And then since 2012, we're also looking at CTD surveys along both the cross bay and then along bay to look at the estuarine gradients and to look at from the surface to the bottom measurements. And with those CTD measurements, we do periodically water samples at surface and depth, which are right now getting analyzed. Thank you very much to Allutic Pride for doing those with the percolator. So, and then just so to go through some of the pieces here. Is this not? Did that slide advance? There it goes. So just the long-term monitoring from the Ketchikan Bay NER water quality station. So just, you get that sense of where we've been sitting over time with the heat wave in 2014, 2016, so temperature anomalies, and then 2019 being warm again, having that cold blip in 2020, and then warming back up relative to the long-term means. Along with those sensors, while they're not the quality of any of the measurements that are being made now, were pH measurements. And so you have kind of the temperature, the salinity, the PAR, all of those in the long-term context from these water quality stations. And the piece that I think is really quite interesting when you talk about relative to GAC1, when we did the comparison of the climatology from the near surface GAC1, so about 25 meters from the long record is what we got, and the near bottom station at Seldovia salinities are saltier every month of the year on average than the near surface GAC1. So that says something interesting about the sources of the water. And anyway, that's something we're tracking over time within the Gulf Watch Alaska program. But there's some interesting connections here that I think is going to tell us a lot about the system as a whole. And then just showing some of the patterns that we see from the CTD surveys. So these are year round. We're doing them monthly. We've been doing them since 2012 monthly. So it's a good climatology now. That's just the temperatures from 2012 to 2020 here, surface to depth. This is at the mid-bay, one of the stations along the mid-bay transit. So it literally is like right in the middle of Ketchikan Bay. And just showing some of the patterns from at depth, but then at the surface and at the bottom here, we are also periodically collecting water samples for carbon chemistry. So then that paired with what then Amanda is doing with the 5 sensors now is really giving us a good picture of variability on different scales. And as several people have mentioned here, and showing some things that Hale and Amanda have in the LNO paper that was just published, congratulations. It's that extreme variability, both with driven by the biology and the photosynthesis with the phytoplankton blooms, as well as for us by tides. And then spatially as well, because they saw changes in the timing of when things were more variable in conditions at the head of the bay, which has more glacial water influences, than in Jackaloff, which is sits in the outer bay. So just looking at that in a couple of different ways. I'll also note that our lab host, Amanda, has set up a experimental OA system to kind of pair the responses of biology. And it's a fairly simple system. It's not what they have at Kodiak, but it does give us the ability to do some of the experimental work. And Marina talked about that at the AMSS talks, if you haven't already seen that, and I think has an update later on. And then just a piece, I guess I'll pull out here because the earlier talk made me think about it, is that we also do a lot of kelp ecology work at the lab, mainly through Brenda Konar and Katrin Eichen at UAF. And that links into some of these studies about how are we mitigating higher CO2 levels with macroalgae. And I'm going to make a bit of a shift here. And this is, I think a bunch of you were in the HAB OA workshops that NOAA put on in August and the webinars before that. And this is more for conversations going forward. But this thing about how we're intersecting, if you look at the lens of in the near shore, oyster farmers, subsistence harvesters, and that, you know, it really is, we sort of had this thinking about, well, what's happening now, you know, what are their concerns and going forward? And it's kind of what, it's like what you're doing, Yvette and others with the council, right? But this is now on the nearshore stakeholder side. And really what came out, not just for our region, but across all the regions nationally, is really this intersection between OA, HABs, and climate change, and needing to get a handle on, you know, when is it going to affect us? Do I need to be worried now? What's the first thing I need to be worried about? And getting this, again, I'm kind of going towards that synthesis of information to address these questions for the species that folks are interested in. So just that was a very big discussion from that workshop for those who weren't able to attend it. And then this was just one other fun, this is my comment on the variability that we're trying to get a handle on, right? You know, 2019 was really hot and we're like, oh my gosh, we're moving into the next heat wave. And then, you know, January came and we plunged right back into cold really quickly. So I think it's great that we have the ability right now to be measuring through these different scales of variability from, you know, biological to physical to climate. Thanks.
Thank you, Chris, and thank you also for bringing up those topics on your second to last slide, which I think are ones that the network will be really working to address, or members of the network, I think, in proposals that are coming up as well. I know we're losing Toby at 10. I'm hoping, I know there probably are questions for Chris. Maybe they can go in the chat so just so we can get a quick update on the tipping points before Toby moves on to a next meeting. Thanks, Chris.
Okay, hello everybody. Let me just share a few slides, if I may. So this is actually a really good, Chris provided a really good segue into, can you see the slide? She provided a really good segue into our project, because she hinted towards so the what now, you know, what are we going to do with that variability? How may it relate to management and response to really a changing ocean environment? And what this tipping points in a changing ocean project that we had or still have, it's in its third year of 3 years, and we're delayed by COVID. It's likely going to be another year, for sure, actually another year. This project is really about looking at that response and looking at kind of the capabilities of how can we use all the information that's available from everything, really, taking a systems approach. So looking at the ecology, looking at the species response, looking at our industry and our different parts of our industry in the salmon system, everywhere from harvesters to processors to also managers, and take all the data and try to figure out how we can improve decision making, or at least integrate what we have, the information we have, in order to, what we would hope, preemptively avoid certain catastrophic outcomes, or prevent a tipping point from happening, or simply responding in the simplest way to the variability that we know about in the system. And to give you an example, or to kind of justify why we focused on pink salmon in the Gulf, was certainly from a management perspective, that's very interesting. Obviously, with pink salmon, enhanced management, and that enhanced management in historically hasn't really responded to anything quite like the variability in the ocean or such factors, right? So it was an interesting economic, bioeconomic aspect that we also wanted to look at. And looking at Claudine's model and the modeling in the Gulf of Alaska that was coming along, we thought we wanted to focus on salmon, pink salmon fisheries in the Gulf. And on top of that, doing a lab study also on juvenile pink salmon. So it's a very kind of a bigger project with many different parts to it. And here you could just give you a brief overview how it's kind of all fits together. So what Jan after me, Jan Olberger is going to talk about is the biostatistics analysis that really takes some of the data that's available in the Gulf and looks at, okay, can we identify or synthesize some of the tipping points that we see in the systems in the Gulf of Alaska system. And we want to integrate that research into a bioeconomic model that then looks at kind of the response of hatcheries, the response of our management system to the information about tipping points, also information about juvenile pink salmon growth that we're hopefully this April are going to start with Amanda Kelly in the lab at the Aleutian Pride Shellfish Hatchery, looking at pink salmon growth under future ocean conditions. And we're also right now engaged in kind of a salmon governance analysis. And this is taking more of a political economy view, looking at local control, looking at equity within our salmon system, looking at our current management system and regulations, and looking at alternative management regimes as well that could or may not be options for future management to really be more responsive and adaptive to the changes we see and the changes we predict in our changing ocean. That again leads to the so what, what do stakeholders view of that? What are their attitudes and preferences when it comes to those alternatives or those various policy options? And we're hoping to do a salmon permit holder survey hopefully in the next year. And that all again integrates either qualitative or quantitative information in the bioeconomic model, and also provides it for outreach efforts that Darcy is leading and with decision makers and obviously participants in the salmon sector. So with that, I'll take brief questions if I have another meeting going on, and I'll hand it over to Jan, who's gonna tell you a little bit about some exciting new research that he's been doing in the Gulf.
Great, thanks, Toby. Are there any questions for Toby before Jan talks about the modeling aspect? Okay, Jan, why don't you go for it?
Sure. Can you see the slides?
Yes.
All right. Thanks, Darcy. Thanks, Toby. T has already nicely introduced what I'm going to talk about, so I'll keep it brief. Give a short update on so the time series analysis part of the Tipping Points project, where we're interested in effects of environmental change and competition in the ocean on the productivity of wild pink salmon in Prince William Sound in particular. And we chose Prince William Sound well, for several reasons. One is that there's good quality time series data on wild pink salmon escapements and harvest, and therefore run sizes. That's also the region that has the highest share of hatchery production. So about 50% of the global hatchery releases for pink salmon actually come from Prince William Sound. So we're particularly interested in that region. So the questions more specifically we ask are, is productivity associated with changes in ocean acidification or temperature? Does competition with other salmon or between the brood lines of pink salmon limit productivity, and then are hatchery fish negatively affecting wild pink salmon through competition? And then the data we use, I just like to show the actual data shown here. So the abundance time series for pink salmon in Prince William Sound, where the total bar is basically the run size, the lighter portion is the harvest, and then the darker shading is the escapement for both the even and odd year brood lines. Not much to note here, except maybe there's obviously high variability. All salmon species have really high recruitment variation, and particularly for pink salmon that have a fixed life history and return 2 years where all fish return 2 years after being spawned, variability is generally pretty high. And on the right, I have two metrics of population productivity. One is recruits per spawner, probably more intuitive to look at. And then the other one is the natural logarithm of recruits per spawner, which is actually what we use in the model, but obviously they have very similar variability and trends. And so the approach we use, I don't want to go into any detail. Statistical approach is basically an extended Rickerstock recruitment model with added covariates, which is shown here. And then the covariates we explore changes in ocean conditions, as well as changes in the abundance or density of pink salmon themselves, and then other salmon species. So one of the time series, or a few of the time series we use, are different seasonal and spatial aggregates of PCO2. Those are the data that Claudine just introduced not long ago for both Prince William Sound and the Northern Gulf of Alaska. We also use Gulf of Alaska time series of sea surface temperature anomaly, and then time series of hatchery releases in Prince William Sound, as well as, again, different spatial aggregates of what we call competitor abundance, which is abundance of sockeye and chum salmon in the ocean, either just the Gulf of Alaska or on a broader spatial scale. And then we also are particularly interested to see if there's any changes in these relationships with pink salmon productivity and the regime shifts in the North Pacific Ocean, particularly the 1988-89 ocean regime shift. I don't have too much time to go into detail, so I'm just going to try to summarize what we found so far. So that the very broad picture is that our results suggest non-stationary and interactive effects of climate and competition on wild pink salmon productivity. And more specifically, we find that the spawner-recruit relationship of both brood lines actually appears to have changed around the regime shift, which indicates sort of opposite responses, or changed in opposite ways, so opposite responses to the ocean regime shift. Also, the temperature production relationship changed from positive to non-significant around 1988-89. That's not news. Mike Litzow and others have shown this for other species of Pacific salmon as well. But we can sort of recreate that here. We do not find any evidence for an effect of ocean acidification on pink salmon productivity based on the available data. But it's important to note that these time series were much shorter than our total time series, and therefore probably limited and not conclusive evidence. We also find evidence for competitive interactions between the brood lines, as well as potentially with other salmon species. And then lastly, the productivity of wild fish was negatively associated with increasing hatchery releases, which suggests that hatchery supplementation reduces the productivity of wild pink salmon in this region. Yeah, that's pretty much it. I'm happy to take questions.
Thanks, Jan. Are there questions for Jan? It looks like none right now, but as this project progresses, I think there's going to be a concerted effort to make sure that the information gets shared in understandable ways to both the ocean acidification science audience and also, as Toby mentioned before, there's a significant stakeholder engagement portion to this project. And Molly Mayo with the Meridian Institute is leading up the stakeholder engagement and is going to be starting a series of interviews. Part of this was changed due to COVID, where we can't actually convene participatory groups, but we are kind of trying to take it in a new and positive direction of having some more one-on-one engagement and really listening to fishermen about their thoughts, both on what should go into studies like this and also what they think about some of this preliminary data.
Yeah. Hey, Darcy, quick question. And that was actually going to be this is Chris, my follow-up, I guess, is where that's going or how that's getting to the management side. Like the plans for the engagement on that side, just because that's a super, for big question for us here right now in Keshmak Bay as well.
Yeah, well, I think at this stage in the process, it's going to be meeting with fishing industry, prominent people in the fishing industry to basically share some of this preliminary data and get feedback on what should go back into some of the modeling and the technical side. And Molly Mayo, Molly, I might throw you in here a little bit too, as we've been trying to kind of forge ahead amidst COVID. But realizing that at the end of this, oh, there's Molly. At the end of this project, we're hoping to have strengthened relationships with the fishing community and also like not come up with like an adaptation plan, but more of like guidelines of what the industry, how the industry sees adapting through governance and the part that ICER is doing, looking at right now, like how flexible is fishing management to respond to these types of issues, and what are some recommendations both from the industry and from management on ways that maybe could be made more flexible in the future. Molly, do you want to chime in?
Yeah, I'll say two things. One is that I think you summarized well, Darcy, the fact that we're not trying to make recommendations as much as better understand the options, both from a scientific perspective and from the perspective of the values and interests of stakeholders, and with a particular emphasis, in part just because of scope, a particular emphasis on the commercial fishing industry, but not to the exclusion of others. And to your point about managers, the decision makers and overall resource managers, at the outset, the framing is more around making sure that we understand what will be helpful to them and making sure that they understand what we're doing so that the two can kind of come together. What comes out of this study can help to inform their thinking so that it's relevant to their decisions and the questions that they have, et cetera. And basically is what I'd call the not the beginning, but the continuation and maybe the enrichment of that dialogue, that conversation with decision makers. It seems, and we did have a meeting with the Board of Fish. It feels like forever ago, but anyway, I think it's important, and everybody on this call is probably well aware of the fact that interest and awareness is increasing significantly, and including managers are talking about this more significantly. And the Board of Fish was very clear in saying that they wanted to stay apprised and they would like solutions as opposed to just understanding the problems. Come back to us when you have some sense of some solutions. So our goal is simply to keep the conversation going. We won't be able to answer all of your questions.
Thanks, Molly. There's probably more questions about that. Hopefully for now they can go in the chat as we're moving along on our agenda. The next is Andy Wall from the Kodiak Area Native Association talking about Kodiak area community monitoring.
Here, let's see if I can get the right one to pop up, everybody. Can you see my PowerPoint?
Yes.
Okay, terrific. Is it the presentation mode one or the full screen one?
It looks like full screen.
Beautiful. Okay. Thank you, Zoom. All right. So hello, everybody. My name is Andy Wall. I'm the environmental coordinator for the Kodiak Area Native Association, also known as CANA, on Kodiak Island. And my PowerPoint here says a Kodiak regional update. It's going to be specific to tribal community sampling. I know a lot of people have mentioned other efforts that are happening in Kodiak, and we do have quite a hub here for ocean acidification, but I'll solely be focusing on the tribal research. And so there's 10 federally recognized tribes on Kodiak Island. And in about 4 years ago, CANA received EPA IGAP consortia funds to assist the tribes on their environmental priorities. And through conversations with the tribes, one of those main priorities was identified as ocean acidification and water quality monitoring. So the environmental coordinator at the time knew that Kodiak was this hub of OA kind of working, and worked together to create this program. And also giving credit to other efforts around the state, as Sitka and Alutiiq tribe, and Alutiiq hatchery, excuse me, because they really helped guide this program. And this program started about three years ago. And the main focus is, marine chemistry changes and impacts on subsistence resources. So there's 7 communities on Kodiak Island, 6 of which are located off the Kodiak Road system. And so you'll see there are 5 red stars here for active locations for ocean acidification monitoring, and then 2 yellow stars down on the south at Akiak is pending, and also at Katoy Bay, that's a hatchery up on a Fognak that is pending, wanting to get started researching ocean acidification in Kodiak. And there's also some locations with Blue Evolution kelp farms that have begun collecting ocean acidification data. And there's kind of the 2 efforts that are happening. There's discrete sampling, and then there's also a percolator in the Kodiak NOAA lab. That's the first location that you see at the top, South Trident Basin. The floatplane dock is a discrete sample location and also has the continuous data set from the percolator. So there's quite a bit of efforts happening on Kodiak in general. And when we work to establish these sites, the programs that kind of came to be is using a YSI and a Niskin to collect surface samples at a depth of 0.5 meters, and 1 meter above the bottom of the seafloor. So we're hoping to get a comprehensive data set of what's going on in the water column, and the ideal circumstance is collecting water samples every Wednesday at the same time in the same location. But there's been a lot of hurdles over the past year, like many people have already mentioned, about collecting these samples. There's been a lot of staff turnover. Many of the people who helped establish this program have since left, and so have kind of, it was established and then a lot of people left, and so we were regaining momentum, and then COVID happened, and a lot of the communities that were collecting samples, those locations had to be put on hold because the NOAA facility is operating on a skeleton crew, and the mercuric chloride that is needed to fix these discrete samples has not been able to been sent out for the last 9 months. And so we've been able to have the percolator up and running through NOAA, and to be able to continue samples through NOAA as well at South Trident Basin for discrete data set. But all of the other locations have been on hold. And so there's a couple of workarounds that we're, trying to figure out. CANA is trying to take on the responsibility of shipping the mercuric chloride, and hopefully that will be able to get the program kind of restarted. But it's also allowed us, kind of this downtime has allowed us to revisit some program aspects that we can improve on. And so one of those is people were collecting data for roughly 1.5 years, 2 years, and not a lot of data was being pushed out to the communities and the tribes who were collecting this data. So over this last winter, we were able to put out the first preliminary results. And this is the Kodiak continuous data from the percolator from April 2019 to February 2020. So the top panel shows PCO2 measurements, the middle panel shows salinity, and then the bottom shows sea surface temperature. And then we were also able to give kind of individual communities updates on what their data looked like. Because what we found was, okay, great, we have this program, but there was a lot of lost momentum in the communities even before COVID, because we weren't getting that data back to community members. And so that's really been something we've been trying to work on and re-energize. And then also, because Kodiak has so much ocean acidification work that's happening, we're hoping to host kind of Kodiak specific ocean acidification meeting where all of the people working on OA in Kodiak can meet up and really talk about our efforts and figure out, you know, how can we combine our efforts and share data and move forward as kind of one unified effort. And so that's a lot of really great hope that's coming, and we're looking forward and hoping to get the program restarted. Kind of going off of that hope and re-energizing efforts feeling, we are planning the 3rd annual Marine Water Quality Workshop. And the workshop is a 2-day workshop. One day is focused specifically on ocean acidification, and the second day is on harmful algal blooms. And this is strictly for tribal environmental coordinators and leaders to receive training, provide feedback on the programs, and get kind of one-on-one or small group access to expert panelists and presenters to be able to talk about these things that are affecting the tribes and communities. It is going to be virtual this year, but we're hoping to make it exciting and engaging. It had to be pushed out until February, but that's kind of where a lot of our energy and focus is going in. And then we have also working to create sampling videos to assist with some of the lack in in-person training that was able to happen this year. And so we've been able to create a video on how do you collect the samples with the YSI and the Niskin, a separate video on how do you fix your samples with mercuric chloride, making sure we're taking accurate safety precautions with the guidance of NOAA, and also kind of a video about what happens when those samples come back to the NOAA facility, really to provide a comprehensive picture to our samplers of like, okay, you're going out every single week, you're doing this work, and really here's how it matters, and providing the results and feedback to those samplers directly. So it's been a little bit of a rocky year, but there's a lot that we have to look forward to, and there's a lot that we've been working on. And so again, thank you for the opportunity just to kind of share the efforts, some of the efforts that are happening on Kodiak Island, and look forward to hearing the rest of the talks from people today and answering any questions people might have.
Thanks, Andy. Those videos sound like they will be helpful to probably many people, not the Kodiak area, but also others that are interested in like what actually goes into all this. And I know there's kind of an effort right now to create more video around the topic of ocean acidification. I know Alutiiq Pride is trying to do the same thing. Jeff will probably mention it, but I think, yeah, the more that video is so powerful as a communicatory tool. So thanks for sharing that. I think realizing that we still have a number of presenters left, I'm thinking that probably the best thing to do now is to put questions into the chat. And if you've just presented, please keep an eye on the chat and maybe start answering questions over there so that we can keep it flowing. It would be great if you do have questions for the presenter to put it in so that everybody can see it, because if you have the question, it's likely that other people would appreciate the answer as well. So let's see, next we'll move to Jacqueline Ramsey at the Alutiiq Pride Shellfish Hatchery, talking about the ocean acidification activities there.
Hi, can everyone hear me?
Yes.
I'm having intermittent issues and my video is not great, so I am going to go ahead and shut off my video here.
Sure.
Hi, everyone. Can you see my screen?
Not yet.
How about now?
Yes.
Great.
There we go. Yep.
So I wanted to, talk to you a little bit. Let me just try and get back to my first slide here. Help me out here. Do I need to just from current slide, beginning? So I want to give you an update on measuring the carbonate systems in our coastal waters of South Central Alaska with our citizen sampling. Right now, on the screen, you're seeing a small section of Alaska, the South Central portion, the Kenai Peninsula, where we have some of our sites that I'm showing you here. We have Eyak, Chiniga Bay. We hope to be adding to Titlik. We have Valdez. Our Berkelator, of course, is located here in Seward. Chiniga Bay, Port Graham, Nanwalek, and we also have Seldovia, which is not on this map. The Alutiiq Pride is a division of the Chugach Regional Resources Commission. We're a nonprofit intertribal fish and wildlife commission, and we're devoted to tribal natural resource issues. Alutiiq's been monitoring the carbonate parameters of our incoming seawater since 2013 through collaborations with the Burke Hills at OSU and Wiley Evans at Hackeye. We installed the Berkelator. And have been monitoring our seawater, like I said, since about 2013. With the Berkelator, we were able to expand our monitoring program to include monitoring coastal waters of our villages. So now we're going a little bit beyond. We have a few sites out in King Cove. We have a site in King Cove, and we also have partners in beyond up in Barrow, Nome, and Kotzebue. We hope to expand with the goal of characterizing the seasonal variability of their local carbonate systems as well. And also in order to characterize the seasonal trends for those sites. Hopefully the data sets could help assess drivers of those trends that may be specific to different localities. This is a shot of a few of our samplers. This is Port Graham, this is Seldovia, and this is a group of our samplers with our hatchery people as well, myself, Jeff, and Chelsea, and 3 of our samplers from the tribes. And from their samples on a weekly basis, we're able to get a profile for their specific locale. This is a small sample set from Seldovia that shows the aragonite saturation levels over time along with temperature. Aragonite on the right, temperature on the left. And in order to do so, we require the samples to be acquired according to very strict guidelines and protocols. We called on PMEL and Hackeye and OSU to guide us in those protocols. And what we are able to return to our tribes are the DIC system parameters of aragonite saturation, and calcium, carbon ion, dissolved carbon dioxide. We use CO2 sys software for that. Wiley Evans, of course, is our guiding PI for our monitoring efforts and a very large part of our sampling efforts. So this is new, all coming together, 5 years of this series that we've been doing. This is data that is most of our partner villages, sites in the South Central area. And so we have cruises as well as citizen sampling data in this 5-year time series, which the details, if you have any questions on, can be directed towards Wiley, who's here, thankfully. And I just wanted to also let you know that, or kind of point out on this axis is temperature, we have salinity, PCO2 and TCO2. Again, a 5-year time series with some time series data that's just a small, maybe 1 year here and there. And this is Valdez data, I believe, and it's quite an outlier with small aragonite saturation near zero due to the incoming fresh water. So I just showed you that time series for TCO2, PCO2, salinity, and temperature, and then we'll move into the saturation states. Just again, I just briefly want to show these slides to show you the variability that we're seeing over time in South Central and how it kind of tracks. These data points are cruises. That's why they're kind of stacked on top of each other. And what I wanted to show you on this slide is in the aragonite saturation plot, we have a gray line here at 1.5, and down here in the calcium plot, we have a 1.0, but it is in the 1.5, that kind of shows you that a lot of the times our sites and our stations are above that saturation state. Let me just make sure I've covered everything I wanted to on that slide. At our sites, like I said, our samples are taken, monthly or weekly. And then once a month, we usually have our samplers take triplicate samples so that we can deduce what's going on with their sampling. I did want to also point out one other thing, but I can't quite find it right here right now, so I'm going to move on to say thank you. Our COVID has not really stopped all of our sampling. Some of our samplers are having issues out in the field with being able to get into their facilities or whatnot, but in a lot of cases they are prevailing. And here at the hatchery, we are also taking our precautions, and we've been able to manage through this situation, which is very, very nice. In the future, what we've got going on right now, we have a lot of projects going on at APSH. We have a large kelp production project that has been underway for a number of months. We're going to be moving into a salmon project for tipping points and OA. Right now, we have a PCO2 sensor that was developed by Burke Hills, which is another project that we're doing to kind of put that sensor through its paces and get it calibrated to the BOL. We have clams and clam out plants on our radar screen, as well as we're beginning to ramp up a HAB lab for harmful algal blooms. So with that, I think I'm going to go ahead and say thank you and take any questions or move on as needed. Thank you.
Thank you, Jacqueline. A lot going on at Alutiiq Pride these days. This segues really nicely into the next talk by Wiley Evans at the Hakai Institute, who's going to be talking about that time series data from the Kenai. And I just want to mention, I see a question from Russ Hopcroft in the chat, and we can just use the chat right now to answer those questions, or perhaps Wiley will answer them in his.
I'll answer it so yeah, the answer is yes, Russ, for both those. So Jacqueline, if you can stop sharing your screen, then I can go ahead and share.
I'm trying to stop sharing my screen.
Might be able to help with that. There we go.
Oh, good. Thank you.
Okay. All right. Thank you, Jacqueline. This is perfect segue into what I want to talk about. I want to talk about 3 time series that we're generating around Kenai Peninsula. One, obviously, from the Gackoa mooring, so our longest CO2 time series in the state. The second from the Allutic Pride percolator that Jacqueline was just mentioning. And the third from the Saldovia Village Tribe, so one of the community tribe time series that we're generating. And before I get into the time series, we've talked a lot about variability so far this morning. And so I want to highlight this equation, which we should all know and love, which is, I think, the most important equation to describe CO2 system variability. And so what we have here is variability in CO2 driven by these terms: changes in temperature, changes in salinity, changes in total inorganic carbon, and changes in alkalinity. The change in these terms is driven by these processes. And so they're color coded to help you understand, but warming increases in temperature, increase PCO2. Freshwater addition decreases PCO2. Net community production decreases total CO2 and decreases PCO2. Physical transport, which usually consists of mixing high CO2 water vertically to the surface, increases PCO2. Calcification decreases alkalinity and increases PCO2. And finally, gas exchange for undersaturated waters would increase PCO2. Okay, so these 4 terms on the bottom, we can collectively call the biophysical terms and separate them from the temperature and salinity effects. And so I'll get into that in a bit. Here's the time series from these 3 sites, and they're fantastic. So the top plot is the temperature, next plot down is the salinity, and then we have the PCO2. The red is the Gackoa mooring, the black is the Allutic Pride percolator, and the blue is the Saldovia Village Tribe time series. So really awesome seasonality in the Gackoa and Saldovia time series in all parameters. Some seasonality in the Allutic Pride time series, but it's more muted because the Allutic Pride seawater system has an intake of 20 meters that's fixed to the bottom. And so there's a lot of high frequency variability, which I know Kale and Amanda know a lot about. So this is tidally driven because it's a fixed intake at the bottom. There's also some low frequency variability as well. So some events appear in certain years and not others. And you can see the most recent data from Allutic Pride shows some conditions that we haven't yet seen before. But we can take these time series and calculate some really simple statistics to compare them. And the way I calculated these statistics is exactly the same way that Adrienne Sutton did in her mooring paper using all the NOAA moorings. And so in order to sort of make it comparable with what Adrienne did, I calculated the same way. And so we have the seasonal amplitudes from all 3 sites and estimates of the interannual variability. And you'll note that the Gackoa mooring and Saldovia time series have near equivalent seasonal amplitude. That's the change from winter to summer. The interannual variability seems larger at the Saldovia site than at the Gackoa mooring. Saldovia site is 4 years, I should mention, so that may be part of that contributing to that larger interannual variability signal. The Allutic Pride record, on the other hand, has a much more muted seasonal amplitude, so it's much smaller with larger interannual variability. So there's some unique differences between these time series. So now we can pull apart the components. Okay, so the top plot here is the temperature component of the CO2 variability. And so, as I said in the beginning, when you warm the water, you increase CO2. When you cool the water, you decrease CO2. So you have this nice seasonal oscillation just from warming and cooling. So summer warming and winter cooling. The second plot down is the salinity effect. Okay, so Gackoa mooring, that surface measurement is right at the toe of Bear Glacier and gets a lot of glacial meltwater. And so you can see changes in salinity drive big change in PCO2 at that site. There's a more of a reduced salinity effect at Allutic Pride, and actually at Saldovia, it's a little bit more erratic. It seems like there's a salinity impact in the spring, and then a little bit of a lull in the summer when things are pretty dry, and then perhaps another salinity effect in the fall when the storms kick up again. But what's important here is that you don't have these 2 effects happening in a vacuum. So you have fresh water coming in that's also warming up. So you add these two components together and you can see that the salinity effect actually gets reduced when you add in the component of warming. And so summer warming offsets some of that summer freshening. Okay, so now you can take this combined TS component and subtract it from the observations. And what you're left with is that biophysical component. Okay, and so the biophysical component is shown on the top plot here for the 3 time series. It shows nice, large oscillations driven by the combination of net community production, physical transport mostly. Calcification and sea air gas exchange are probably minor contributors. And now we can look at, okay, what's really important? And so we can take the ratio of these components. So the ratio of the temperature and salinity component to the ratio of the biophysical component. And if the ratio is 1, those two components are equal. If it's more than 1, temperature and salinity drivers are more important. And you can see the ratios for each of these time series is less than 1. So the biophysical component is the most important component for driving variability in these 3 nearshore time series. And so with that, I'll stop right there. Thank you.
Thanks, Wiley. Questions for Wiley? I guess I would be curious, Wiley, if you were talking to a community sampler who said, so what about that? How would you respond?
Well, I mean, so what is, well, I guess it's my own take on what so what means, but I guess, you know, what it means is that the contributions from the local biological community, so driving the net community production, and the contributions from the physical transport are much more important in these settings where these 3 time series are than, say, glacial melt. And I think that's probably pretty important to understand. Sort of thinking back to Jacqueline's slide where she had compiled all the discrete sample data and Valdez was a clear outlier. In Valdez, that's not the case, but in all the other sites, it is. And so when we think about that complexity, I think we need to make sure that we portray that, because making statements like, you know, the entire Gulf of Alaska nearshore environment is dominated by freshwater influences is wrong.
Thanks.
Yeah, Wiley, this is Chris. That's just a really good point that you know, Amanda's been showing that, and it's interesting to tease out the details of the variability of that spatially. Thanks.
Let's see. So up next is Will Peterson at Sitka Tribe of Alaska.
Thanks, Darcy. Thanks, Wiley. Can you guys hear me okay?
Yes, I'm good.
Awesome. I'm going to keep my video off because I'm having some connection issues. So my name is Will Peterson. I'm an environmental lab specialist here in Sitka for Sitka Tribe of Alaska, which is a member of the Southeast Alaska Tribal Ocean Research, or CEDOR. And I'll give a quick update on our ocean acidification baseline data collection and a quick timeline for people who may be less familiar with our program. STA established our OA laboratory in 2016 with help from Burke and Wiley. And in 2017, well, maybe it was later in 2016 and 17, but the percolator came online in the second half of 2017. And that year we collected 80 discrete samples in Sitka and Hoonah. 2018, we upped our effort throughout the CEDAR network, and 7 communities collected about 370 discrete samples. 2019, we also upped our effort a little bit, and 2 communities came online in addition, and we collected 380. And despite COVID and everything, until 2020, we also maintained our effort with about 375 discrete samples. And so our guideline for discrete sample collection with our partners is collecting every week and a triplicate once a month at the beginning of the month. Also in Sitka, with our percolator, we're collecting continuous PCO2 data. And here you can see about 4 years of data starting in the summer of 2017. At the top is the PCO2. And this is sea surface near shore. So we're collecting about 3 meters depth, and it's collected at Sitka Harbor. So this is pretty unique data. It's a lot of mixing with, you know, boat traffic and fisheries and float planes. And so that might be interesting in itself. So this top graph kind of shows a good seasonal variability. You can tell, and this gray line is the atmospheric PCO2. So you can tell the occurrences of the spring blooms pretty clearly, and then die-offs over the year, and then PCO2 drawdown again. And luckily this year, or 2020, we were able to capture that spring bloom despite being sent home in March. I was able to keep the percolator running for a few weeks, and then that had to stop because I had limited capability to maintain the lines throughout the bloom, and our mussel buildup was quite immense. So that posed some challenges, and you can see it's a big gap here because we spent about that whole time cleaning and fixing the line. Well, it sat for a couple months, and then once we got back to the office, we were cleaning the lines and removing mussels in vast quantities. And so that was a challenge, but we got it back up and running in September, and it's continuing to run pretty well. In the middle graph is salinity, and the bottom is sea surface temperature. A little bit about our discrete data. We've collected and analyzed, well, we've collected over 1,000 samples and analyzed about half of those. And so these graphs are just of the Sitka data. And so you can see this is a day of year format, so all the years together. There's some good consistency between the 3 years of data that we've collected with discrete samples. This is PCO2 in gray, and then temperature in green, omega aragonite in the brown, and the line across here is saturation state of 1. So most of our samples are above, but you can see it dips later in the year. And in blue is pH. And so that also follows in late October, pH tends to dip. So one of the things that I'm pretty happy about that we did this year, despite COVID and all that, we were able to improve our discrete sampling method. So one of the challenges with being a network of tribal samplers, you know, separated by distance and using, small air carriers is that transporting sensitive materials with mercuric chloride in them can be difficult, especially when the carriers may not handle the packages very carefully. They may not know what's in it all the time. So to prevent any damages to our product, we designed these discrete sample kits. And so what you see here is basically an action packer. And thanks to our technician, Nicole, she was able to put together these little custom foam holders for the bottles. And so we can hold about 20 samples, 16 to 20 samples, depending on the design we use, but this one's 20, I think. And that allows us to greatly reduce the risk. These can't fit in a freezer, so that the shippers won't put them in the freezer. There's less breaking and spillage. And we also implemented a sampling sticker on the right. This picture on the right, you can see our old method of taking our data was using tape. And we found that it was kind of inconsistent between samplers. So we're now supplying all our bottles to our samplers with a pre-labeled sticker. And so that should help keep a consistent log of data, site name, date, temperatures, any other information. And it really helps out when we're reusing these bottles. These stickers actually come off really easily and there's less residue. So it was really great to do this year. Other simple improvements we've made were including a temperature probe in our inlet so that we can verify the, I guess, the efficacy of our data. And we're continuing to try to develop our education efforts. So we presented to students at the middle school this year. Despite COVID, we were able to do a virtual tour, so that was really great. We developed a training video for samplers, and so that's a good improvement. Yeah, we're continuing to sample, trying to crack at that backlog of samples. We have about 600 to 700 samples waiting to be analyzed. And yeah, thanks for listening. If you have any questions, this is my contact info at the bottom.
Great, thanks, Will. It's really exciting to see the amount of data that is being produced now that we're a couple years into some of these sampling programs, and also the outreach efforts made by these tribal programs to really bolster engagement and feeling connected. So thank you.
I agree. Thank you.
Realizing we're rapidly coming up against 11 and we still have a number of talks. So I think we'll probably end up going a little bit longer than we thought. I know that people are eager to hear some of these updates. So we'll try to make sure that everybody's sticking to 5 minutes and questions can go into the chat. And we're going to move over to the species response side now. And we'll hear from Nita Benarsek on pteropods in the Gulf of Alaska and Bering Sea.
Right. Can you see my presentation?
Yes.
All right. Notice. Okay, let's start from the beginning. So this is really a project that has ended a year ago, funded by North Pacific Research Board Council. And the aim was to try to assess the risks of ocean acidification. In this particular case, we're using pteropods as indicators, and we are focusing on the Gulf of Alaska and the Bering Sea. And this is really a multidisciplinary project and effort. And so obviously it's not just my work, but we have modelers like Claudine and Darren in here, chemical oceanographers, genetic people, and so on and so forth. So really a multi-effort in order to assess the risks. And the framework we try to use in here is really get a grip of the exposure, sensitivity, and adaptive capacity, because without any of these components, you can't really have a good understanding of the risks. So when we are talking about the exposure, we are thinking of coupling natural variability with climate change trends and effects, also some additional anthropogenic inputs that can go into the models, for example. So the exposure then impacts the sensitivity. From the strategic point of view, we are trying to use the most sensitive species and most sensitive processes like shell calcification, so processes that are first responding to ocean acidification, and also try to establish the connection to the population level processes. Leveraging the sensitivity is obviously an adaptive capacity when we are thinking of the plasticity, genetic variability, but also just the spatial connectivity. So how the movement within the certain environment can help or damage the species to avoid the risks. So in that sense, then, let's go to the results straight away. We tried to characterize the exposure in the Gulf of Alaska. So these are the model outputs from Claudine, and obviously we are seeing the seasonal differences in aragonite saturation state with OA, more severe OA conditions, obviously in the summer. But we really start to understand how much these habitats have changed by looking at these outputs from the 1980s onwards. And we see that we have currently significantly more OA exposures for the species than just in comparison from a few decades ago. So these habitats are really rapidly changing and are under major stressors. When we're talking about the OA exposure in the Bering Sea, obviously there are seasonal differences. I'm not so much interested in that. From the biological point of view, it's really important to understand that a huge extent of the Bering Sea, especially in the summertime conditions or wintertime conditions, is close or below the saturation state. And this is a critical state for a variety of economically and ecologically important classifiers. And our classifier of choice are pteropods. They are now known as really good OA sentinels. They are pelagic snails for the ones that do not know the pteropods. And their shell is really thin and it's made of aragonite, and they can easily dissolve under less saturated conditions, as we can see from these pictures. Especially in these high latitudinal habitats, they are really important food for a variety of different fish species, especially salmon species in the fall time when, for example, these fish, larvae, so juvenile fish, do not have anything else to eat, and then they're basically foraging big time on pteropods. So two important components why pteropods are important in these habitats. So looking at the sensitivity point of view, we know that this dissolution is an important parameter, and we have actually found quite a lot of pteropods, especially in the region of the central and the western part of Gulf of Alaska, to have severe shell dissolution. And this dissolution corresponded with the depth of aragonite saturation state. And so here we also use basically the data, oceanographic data from P16 cruise, that you could see the A and B line in there. And so with the shallower depth in the central and the western part of Gulf of Alaska, we are seeing more severe and larger extent of more severe type of the dissolution. So here's where you can see how the modeling and observations and biological observations are all put together. Okay, but on the other hand, where we're looking at the adaptations, right, one would expect, okay, so if the shell dissolution is so prevailing, how can pteropods actually sustain their shells? So using microcomputed tomography, we were measuring shell density and the thickness, and we have seen that that increases. And obviously that is an adaptation to more severe OA conditions, and we can talk to a certain level of phenotypic plasticity, but on the other hand, be aware that only a part of pteropod population is doing this, so thickening their shells. The other part is actually not doing anything or is declining in shell density. And we also have to be aware that this carries specific energetic expenditure, because these are important energetic costs for the organisms. We've also looked at the genomic or genetic responses, and we have found a pretty uniform population structure in here. So that doesn't necessarily speak to a large scale of adaptation in pteropods. So just to sum up, we have identified regionally specific risks related to OA and pteropods. And we think that this integration, the approach we're using, really improves the prediction of the ecosystem change. And that is relevant for the fisheries and resource management in these high latitudinal regions. And also, we are now at the stage where pteropods can be used as an indicator for monitoring of ecosystem health in the high latitude environments. And because they have very similar sensitivity with the other species, I think they could be a predictor of how the other aquaculture important species are doing. So having this proxies of what's going on in the natural environment, maybe measuring it on pteropods could actually be really useful. And for the next steps, I would suggest that we strengthen the links to salmon and see how the correlation between the pteropods, for which we are actually expecting the decline in population probably in the next decade or so, how that could potentially impact salmon species. All right, That's my 5 minutes. So contact me if you have any further questions.
Thank you, Nina. I feel like there are going to be a lot of questions, and also thanks for like that lead into future collaborations and research areas that we need to focus on. Please put questions in the chat, and I think we'll need to move on next to Lauren Bell with UC Santa Cruz on ocean acidification impacts on kelp species and abalone.
Yeah, thanks, Darcy. Can you guys see my presentation okay?
Looks great.
Great. Yeah, great to join you all. My name is Lauren Bell. I'm a graduate student in Dr. Christy Croker's lab at the University of California, Santa Cruz. And I've been helping to spearhead the year-round research program that our lab has been running in Sitka Sound, where we've been considering impacts of ocean acidification on giant kelp forest communities here at the northern edge of their range. So we're really interested in the effects of acidification to these kelp forest ecosystems, really because they function as both important habitat and as food sources along our coastlines. And of course, ocean acidification is likely to impact seaweeds and the consumers that eat them in very different ways. So our research is focused on how these interactions among species may end up changing in the future. So since 2015, we've maintained a number of pH sensors in these kelp forests, and we've paired this continuous environmental monitoring with seasonal community surveys and with laboratory experiments to test the impacts of future ocean acidification and other stressors on kelp forest organisms. So today I'm really just going to focus our work on our work with abalone and seaweeds, and just kind of give you an overview of the projects we've been working on. If you're interested in our research looking at ocean acidification and herring roe, you can check out our presentation under my name in the Gulf of Alaska Day session from earlier this week. So I'm happy to report that the first publication to come from all this work was released last year in Global Change Biology. So this paper presents the first few years of our environmental and community data, and it captures the big seasonal swings that we observe in both the abiotic and the biotic factors in this system. And I wanted to comment how cool it is to see all the presentations today and in the last year on coastal ecosystems and carbonate chemistry. I'm just reflecting on not that long ago, a couple of years ago, sitting in the NPRB offices and everyone saying, you know, we don't really have much data on what this variability looks like in coastal ecosystems yet. So it's just so cool to see it had blossomed so far in just a couple of years. So the other thing that this paper presents is the results of one of our first experiments that we ran that looked at the effects of ocean acidification on pinto abalone, and how these effects appear to be mediated by the composition of their diet. So the takeaway that we found is that a less diverse diet actually increases abalone vulnerability to the stresses of acidification, and that this is most pronounced under winter conditions, winter pH conditions. So this first experiment really highlighted for us the importance of considering how ocean acidification is going to interact with these other strong seasonal factors at our high latitudes, of course, such as temperature and light availability and nutrient availability. So along those same lines, we have another paper in prep now that considers the effects of acidification with, again, these seasonal abiotic interactions on two species of reef-forming coralline algae. And spoiler, it appears that these calcified algae are particularly vulnerable to dissolution under acidification when light availability is low, such as in the wintertime. So another indication of the importance of season on these species' responses to OA here in Alaska waters. Last year, we turned our attention to fleshy macroalgae, so in particular 3 kelp species that dominate the primary producer biomass in the giant kelp forest here in Sitka Sound. Again, we were interested in simulating these seasonally relevant scenarios of future global change, so we ran experiments in both summer and winter to detect the effects of acidification and warming on seaweed growth, on elemental composition, on chemical defenses, and on their palatability to consumers. And we're still working up the data right now, but preliminary results are revealing that the variety of impacts we can detect appear to be both species dependent and seasonally specific. So this potentially has implications for future composition of what these seaweed communities are going to look like. And given, again, that they're both an important habitat and a major food source, we can imagine that changes to that community composition could be pretty significant in impacting the rest of the food web here. This year, the plan is to take what we've learned so far about impacts of acidification on physiology of kelp forest grazers and on seaweeds independently, and then integrate these effects across this consumer resource interaction. So the big question for us is whether any of the changes we're seeing to the nutritional quality or to the chemical defenses or productivity of these seaweed food sources is ultimately going to be beneficial or actually more detrimental to consumers that are coping with potential metabolic stress under acidification. So Dr. Arlie Muth, who's a new postdoc in our lab, is currently finishing the build for this experiment here in Sitka, and she is hoping to kick it off in the coming few weeks. I'm sure she'd be happy to answer questions if you have any about that. And that's basically our update for now. So I appreciate the opportunity to share.
Thank you, Lauren. A lot going on in the lab. And I also want to mention that Lauren won the Best Presentation Student Award at AMSS this week. So check out her presentation on the AMSS website.
Thanks, Rosie.
We'll move next to Marina Washburn at UAF, who will be talking about chitins. Let's see, Marina, I'm not sure we can hear you.
Sorry, I forgot that part. My name is Marina Washburn. I am a graduate student with the University of Alaska Fairbanks College of Fisheries and Ocean Sciences. And today I'm just going to be presenting some really quick results from the Bidarky project that I've been working on with Dr. Amanda Kelly. And if you'd like to see the full talk, it is, I don't know if they're still up on the AMSS page, but I presented there as well. So this experiment essentially looked at a fully factorial investigation of the impact of elevated PCO2 and temperature on adult bidarkies. And we did this at the OSIS system at the Kasutsna Bay lab, as Chris mentioned earlier. Here we go. So the first result that we gathered was respiration to look at like metabolic expenditure. And over what we're looking at here is the oxygen consumption rate over the course of the experiment, with this being our day zero control. And what we saw is that there were no significant differences between any of the different treatments or across time in terms of respiration rate. So it looks like there isn't any significant increase in metabolic rate. We did see some significance in terms of,
your slides, we're still on your first slide.
How do I?
Oh, it's not in presenter mode. Maybe try putting it into presenter mode.
Sorry, let me try this again.
Sure.
Okay. Can you guys see it now?
Yes, that looks great.
Okay, so this is what I was talking about, the respirometry, sorry, with the oxygen consumption here and then the timing of the experiment on the x-axis. And again, we didn't see any significant differences both over time or between treatments in terms of respirometry. So we did see significant differences in terms of grazing rate. And so again, we have grazing rate here and then the day of the experiment, with this representing our day zero control. We saw that elevated temperature over time resulted in an increased grazing rate. So while there wasn't any differences between the treatments on day 21, we did see significant differences between the day zero grazing rate and the elevated temperature condition on day 21. So also looking at shell composition, and before I show you the results, I just want to preface this with the fact that there are 3 different types of shell present on a Bidarky valve or a chitin valve. And this is lateral shell here, which is the triangular shell, as well as a pleural shell here. It looks like a wing, and then the apophysis. And the apophysis is constantly covered in tissue throughout the course of the Bidarky's life. And so if we look at day 0 results, we saw no significant difference. Oh, excuse me. We did see significant differences in terms of composition between the 3 shell types. So apophysis had significantly more sulfur than the other 2 shell types, and the plural shell had significantly more silica than the other 2 shell types. When we compared our day 0 results to our experimental results, we saw that this pattern of significant differences across 3 shell types was maintained. So the apophysis, the laminar shell, and the plural shell, but that there were no significant differences in composition between the treatments and over time. So while the 3 shell types are different from one another in terms of their composition, they don't appear to be altered as a result of the treatment conditions. We also looked at shell dissolution, and again, it's same format, so our day 0 control, and there's a lot of noise here, but we didn't see any significant results, any significant differences in terms of shell dissolution as a result of treatment or time. So all in all, what our results have kind of shown us, and we still have some molecular work to do looking at gene expression of stress genes associated with ocean acidification and thermal stress. But what these first results have kind of suggested is that Bidarkies may in fact be more resilient in terms of climate change impacts we expect to see, at least on the time scale that we did for this experiment. Again, if you'd like to see the full project, you can feel free to put it in the comments and I can send it to you if it's not on AMSS, but it should still be posted there, I think, through today. So thank you.
Thanks so much, Marina. That was great. And yeah, if you have a link to a link to your presentation, though, maybe behind the firewall of AMSS, we'll send out the full list of those probably next week. Next up is Jamie Mushbach from University of Alaska Southeast on shrimp.
All right, can you guys hear me?
Yes.
Sweet, okay, sorry. I think my presentation should be back up now. Okay, so I'm Jamie Mushbach. I'm a student at the University of Alaska Fairbanks. I'm in the CFOS division at the satellite campus in Juneau. I'm currently pursuing my master's in fisheries and I'm advised by Dr. Sherry Timoni. My research looks at how ocean acidification and ocean warming affects juvenile northern spot shrimp metabolic physiology. So I receive ovigerous females from the Alaska Department of Fish and Game after their annual shrimp surveys in the fall. I keep these females in the flow-through seawater system at the University of Alaska Southeast until the eggs hatch out in the spring. I then rear the planktonic shrimp through their larval stages until they settle out of the water column onto the benthos as juveniles. So the pictures are of the underside of an ovigerous female, the eggs that were on that ovigerous female, the first planktonic stage, and then the benthic juvenile. In order to complete this research, I had to build a low-cost ocean acidification and heating system at our lab here at the University of Alaska Southeast. In order to maintain the pH at a particular set point, I used a pH stat system that was designed by Dr. Kurt Onthank at Walla Walla University. I had the opportunity to travel down to Washington for 2 days and learn how to build one of these monitors with him. And then I came back to Juneau and built the other 3 that were required for my experiment. So these are the pH stat systems or the monitors I built. I used a fully factorial experimental to design to see how ocean acidification, ocean warming, individual and interactive effects on juvenile spot shrimp metabolic physiology. I based my tank pH and temperature set points on the IPCC's prediction of a 0.3 to 0.4 unit decrease in ocean pH and a temperature increase of 4 degrees C by the year 2100. So these are my 4 tank setups: ambient, increased temperature, and increased PaCO2, and then just increased PCO2. I measured oxygen consumption rates of juvenile shrimp at specific time points over the course of a 2-week exposure period to the ocean acidification and ocean warming. And I then calculated mass-specific metabolic rates from these measurements. I also extracted RNA from whole juvenile shrimp at each of the same time points that the metabolic rates were taken. I then synthesized cDNA, and I'm currently working with a colleague in Israel to run quantitative PCR on these samples to look at gene expression. Specifically, I'm interested in heat shock protein 70, which helps to stabilize other proteins during heat stress, as well as carbonic anhydrase, which plays an important role in acid-base balance and ion regulation. I'm currently in the analysis and writing portion of my thesis, so my results will come to follow this spring at my thesis defense. So with that, does anyone have any questions?
Great, thanks, Jamie. It's exciting to see shrimp enter this world of what we know about species response so far. Since we are over time, I'm going to ask for questions to go into the chat, and we'll move to, we have 2 more presentations on fish, and the next one will be Tom Hurst with NOAA Alaska Fisheries Science Center. It looks like Tom's getting queued up here. You guys have been amazing with like being ready to get your presentations up, so thank you for that.
Thanks. Can you see my, let's see, in slideshow now, or?
It looks like it's in, it's not in presenter mode. We can see the slides, but not in presenter mode.
Okay. Well, oh, there we go. Does that work?
There we go. Yep.
Okay. Thanks, Darcy. Yep, I'm just going to give a quick update on a couple of studies with ground fishes that we've been doing at the Alaska Fisheries Science Center and our laboratory down here in Newport, Oregon. This is just a representation of the different kinds of effects that we've been looking at. And some of these you've seen presentations about various aspects, and we'll see another after my talk. But looking at direct effects, food web effects, sensory effects, and then trying to put those together into understanding the cumulative effects on populations. And so just to, as a reminder, we've previously published a number of studies on these 3 species, walleye pollock, northern rock sole, and Pacific cod. And we've seen different aspects of sensitivity in the different species. And so I just wanted to point those out and then give 2 quick updates on things that we've done recently. This is all really early stage work that's not yet published. So with that caveat, in a more recent study on walleye pollock, we found that exposure to high CO2 resulted in a lower rate of fish being able to inflate their swim bladders. So here's some images of the fish. This is when you clear and stain the fish, you can see the presence of the swim bladder here. And when you zoom in on histology, here's the swim bladder. And here's an example of a fish where the swim bladder is not inflated. So it would be right here, but you can see this is the pancreas next to where the swim bladder would be. And over here on the right, this shows the likelihood of the fish having their swim bladder inflated as a function of their body size. So this is a process that happens when the fish are around 6 to 7 millimeters. And we can see that the solid line is the swim bladder inflation rates of fish at our ambient CO2 levels. And the dashed line is when the fish are at high CO2 levels. So there's a real clear effect of high CO2 preventing the fish from swim bladder inflation. And so what we're trying to resolve now is whether or not this is causing a delay in the inflation of the swim bladder, or if this is simply some of these fish just never being able to inflate their swim bladders. There is a very narrow ontogenetic window when they can actually do this. So if they don't do it by a certain developmental stage, they won't be able to do it afterwards. So, so we're trying to resolve that. The interesting thing is fish in theory can survive without a swim bladder, but we know that in previous studies, they have much higher metabolic rates and they can't orient and forage as well. So we would expect them to have higher mortality, but we didn't actually see that in the lab. And so we're trying to figure out if we rear the fish for longer, would those fish without swim bladders end up having mortality later on? So we're still trying to figure out the impacts of this and what's happening with that. So that's one thing. And then another study we've been doing is looking at Arctic cod. And in the top panel, we were looking at the fertilization rate of the fertilization success of Arctic cod eggs. And so we spawned 17 batches of Arctic cod eggs from our laboratory broodstock. And you can see in purple is the fertilization success of the eggs that control CO2 levels, and yellow at high CO2 levels. And in almost every case, the fertilization success was lower at the high CO2. And interestingly, it seems worse among the smaller fish. So this is the body size of the fish. So the consequences of high CO2 on reducing fertilization success was lower at high CO2, and it seemed to be worse among smaller fish. And that's something that will be interesting to explore some more. And then for those fish those eggs that were successfully fertilized, we then reared them to hatching time. And interesting, we did not see an effect of OA on the hatching success of the eggs that were successfully fertilized from among those up top. So these are 4 different batches of eggs that we reared. We couldn't obviously do as many of these batches because of how labor intensive they are. And we had one batch where, halfway through pretty much all the eggs died. But in the 3 batches that were good, we had pretty similar hatch rates across all. So we saw an effect on the fertilization, but once they were fertilized, at least so far, we didn't see an effect on their survival to hatch. So 2 quick updates, and then I'll just mention a couple other things. Other work that is going on fishes. There's a poster at the AMSS Northern Rock Sole larvae, and then Lauren just mentioned her herring egg study, and then Chase is going to talk about coho and salmon, I believe, next. So great. That's it. Thank you.
Thanks so much, Tom. Looks like some positive and some negative and some no effect there. And I want to mention, I know we're losing a few people, but this is being recorded, and I think there will probably be a lot of people accessing this afterwards, so please don't feel like you're losing your audience. Thank you again, Tom. And our last presenter today is Chase Williams with University of Washington on salmon. And I guess, Chase, are you still there?
Oh, yeah. Can you hear me?
Yes.
Trying to share the screen. It's not cooperating. Shoot. Working. Hold on. I'm so sorry.
No worries.
Okay. Working now. Oh. Here we go. Okay. Is that working?
Yes.
Okay, so sorry about that, y'all. So I'm gonna just briefly touch upon what we've been up to and kind of where we're going with. Is this in everyone's way? With our ocean acidification research, looking at salmon and a little bit of sablefish biological responses. And this work has been done in collaboration with Dr. Andrew Dittman and Dr. Evan Gallagher at UW. So, may not go in the next. Oh, there we go. There we go. Okay. So at the outset of this project in 2016, we initiated experiments investigating the potential biological effects of increasing marine CO2 in lower pH waters on coho salmon relevant to Puget Sound. And with the mindset that being an anadromous fish species, we're very curious to see if their response to lower pH waters in the marine environment would be similar to what had been found in other tropical and temperate marine fish species at the time. Mainly being that when these fish were exposed to low pH waters, they showed this significant behavioral alterations, and which was thought to be driven by inappropriate neural excitation in their brain as the fish were compensating for the lower pH in marine waters. So those studies found that indeed, when we expose coho to high CO2 concentration, low pH waters for about 2 weeks, they did show some significant behavioral alterations. The fish in the pH group, about 7.2, that's at 2,700 microatmospheres. They became more indifferent to the scent of the alarm signal, the skin extract and the Y mazes. And comparing that to the control fish or even the coho in the medium exposure, at 1600 microatmospheres, about pH about 7.5, they significantly avoided that scent. So following up behavioral work, we found that indeed in the olfactory bulbs, the central area where odorant signals are processed from the nose, we did pick up inappropriate excitation signals in several areas of the bulb. And that's just a graph there on the left showing 2 example micrographs, the top one being the control fish exposed to an amino acid with a normal response, and then below it, under elevated CO2 conditions, you see the significant increase in neural excitation. And so based on that work, we were also really curious about our marine control fish. So at the same time we initiated the coho salmon work, we also were interested in investigating the effects on a marine obligate species, and we had access to a population of sablefish. And so we did similar exposures on the sablefish. We did behavioral work looking at their responses to a food odorant. They didn't have the aversion to the skin extract like salmon due to their more cannibalistic tendencies compared to salmon. So we used a food odorant to get a robust behavioral response. And again, we did not see, sorry, not again, but interestingly, with sablefish, we did not see a behavioral alteration under the elevated CO2 conditions. And when we did comparative genetic analysis between the salmon and the sablefish, we found that a lot of the neural signaling genes that were significantly altered in the brains of coho salmon were not significantly modulated in the sablefish under the similar conditions, which was really fascinating, but also not surprising. It's becoming more and more understood that the biological responses to these elevated CO2 conditions in fish are quite diverse, as Tom showed in his presentation. And so building off that, we're very curious to the mechanistic underpinnings driving these the responses and the potential tolerance to these low pH waters. So we conducted a small pilot study with some coho salmon as well, and that's the graph here, the salmon blood chemistry data. And we took blood samples at a 0 time point before exposure started, and then following 6 hours, 1 day, 7 day, 14 days, and then after the 14-day exposure, the fish were put in control water for a 1-week depuration, and then blood samples were taken in. And what we found was kind of what we were expecting, a increase in this bicarbonate in their blood. As the fish are exposed to low pH water, they start sequestering more bicarbonate in their bloodstream. And that's exactly what we found. And interestingly, and which is good for wild fish, is these effects are most likely transient. When you put them back in control water, their physiology goes back to controlled conditions. And it's been shown that behaviors as well in fish go back to control-like behaviors. So in addition to some of the olfactory work, another area we are looking at with salmon is in the navigation orientation realm. So the hypothesized signaling pathway that's altered under elevated CO2 conditions is not unique to the olfactory system. It's used in a lot of different sensory and neural processing areas in the brain. And so one area we were really concerned about or interested is the salmon's ability to orient in magnetic fields, with the idea being that in the open ocean, evidence seems to indicate that salmon use the Earth's magnetic field as kind of an internal GPS system to migrate across those the open ocean that don't have a lot of distinguishing waypoints like inland waters or rivers. And so what we did for that experiment at the outset, this pilot work, we had a small cohort of pink salmon, and we built a large 2-axis Helmholtz coil. We put the salmon in this coil and tricked them into thinking they were either in the northern Gulf of Alaska or off the coast of southern Oregon. And then we measured their orientation response to those changes in the magnetic fields. And it was nice to see that our methodology worked. We did get a meaningful response when we put them in the Gulf of Alaska or off the coast of southern Oregon versus the ambient Mukilteo Seattle magnetic field. And so the idea now is to take that methodology and data and then now layer on that ocean acidification component. That was, unfortunately, we don't have that data. That was delayed due to us losing the marine lab at Mukilteo and of course the 2020 COVID restrictions. And so we're really hoping to get back into that soon and build off that work. Additionally, some more experimental headings we're pursuing, especially since we're really interested in these species-specific responses and mechanistic underpinnings of what's going on with elevated CO2 environment. We're really curious to see the differences between salmon species. Again, we chose pink salmon for that initial magnetoreception work, and we want to use them for a follow-up study due to their more marine-like physiology compared to the coho we used in the previous work. So the idea is that the coho have this significant freshwater portion of their life history initially, whereas pink readily enter the marine environment much quicker. And so we're curious if that more marine-ready physiology in pink and potentially other salmon species might modulate that response to elevated CO2 conditions. We're very keen on, and planning to this year, now that we're hopefully going to be back in the lab soon, expanding the exposure scenarios. So getting off just that initial 2-week time exposure we did, but expanding it to more chronic exposures and also building in more depuration components, as well as, importantly, modulating pH over a deal cycle, which is more realistic in the environment, not just a static pH exposure. In addition, we're really want to expand in additional behaviors, not just olfaction and not just navigation. As I said earlier, the neural signaling pathway that was is hypothesized to drive these behavioral alterations is not unique to one sensory system. And importantly, further investigate the mechanistic drivers of stable fish tolerance to low pH waters and the salmon sensitivity to these low pH waters as well. So that includes some of this work here on that's kind of cycling there on the right. That's a section of a clarified salmon forebrain, so a chunk of their brain that we were able to optically clarify. And we stained with phosphorylated ERK, so it's a marker of activated neurons. So what we can do is we can expose a fish to a sensory cue, an odorant, or a magnetic field, and then basically quickly preserve their brain, and we can basically capture in time their whole brain response to a sensory cue and then image that as one whole tissue, with the idea of being able to look for differences in neural activation patterns across the brain. That's one thing with the electrophysiology, which we couldn't do. That's more of a point-by-point measuring system, whereas this gives us the capability to really capture the brain's response as a whole in one go. So yeah, thank you.
Wow, thanks, Chase. This is fascinating, just like the complexity of this species and so many different aspects to investigate. It seems like this is really moving forward. And I remember back to like our first or second statewide ocean acidification conferences and polling the crowd with like a phone app of like what species they were most concerned about, and salmon was the biggest one. And again, 2 years ago at we did a stakeholder survey, and people, as you know, up here in Alaska are really interested in salmon. So thanks for your work in moving this forward. I want to thank everybody for participating today. It's really impressive, the amount of research that's being done on ocean acidification. And the advancement just in the last 5 years is just tremendous. So thank you to all the presenters. You did a great job fitting a lot in and being really smooth with your transitions. We'll be posting this recording on the Alaska Ocean Acidification Network website. If you need to refer back to short presentations, please follow up with the speakers and also forward the recording to your colleagues who may not be focusing on ocean acidification, but may be interested in some of this research. The network will be working on a State of the Science webpage that incorporates much of this research. So I'll be reaching out to individual researchers to make sure that we can basically provide what we know so far on these different topics with some graphics and some imagery and some links to the papers that you've all written. So I'll be in touch about that. I also wanted to mention that the OA network is having a steering committee meeting in February. We're going to be setting the date for that soon. And we are open to ideas of what you would like to see the network take up. Also with regard to outreach, I think a lot of the work that we saw today is probably ready for like a broad audience. The ACAP webinar series is an awesome opportunity to highlight work for a broad audience in Alaska. And then I am also would be happy to work with you individually to share information for relevant, like particular relevant audiences specific to your research in Alaska. And then lastly, I guess if you have students or colleagues that would be like to add, that would like to be added to the OA researcher list, please let me know. And with that, thank you all again. And we look forward to working together in 2021.
Thanks, Darcy.
Stop recording here.